Hello, my name is Jesse Averbukh. I'm a software engineer at Space Telescope Science Institute, and today I'll do a presentation on the color composite images from the James Webb Space Telescope. It'll be about a 10-minute presentation followed by a 15-minute hands-on demo. So I welcome laptops. Just in preparation for that, there is a cloud-hosted version of the notebook I'll be presenting at this link. So you need to go to the link, sign in, and then follow the arrows to get to that notebook. You can also scan the QR code that will take you to this Google Drive. You can go to the presentation, or you can go to the README file that will tell you how to get to the platform. If you would rather use the run the notebook locally, which I very much recommend. It is great to have this hosted on the cloud. You don't need to download or install anything. You just sign in and you can run the notebook at the cost of speed. It takes a long time to run the notebook. It's about 9 images and they total 3 gigabytes. So we get a very nice picture at the end, but it does take quite a long time. So I'll let that load for now. Once that's done loading, if you would rather run the notebook locally, you can follow the install instructions to create a new conda environment, and then you can pip install JDAVIZ. And then with that, you can run this locally. If you instead want to run it in the on the platform, you would need to go here to select the kernel and make sure that you have master class selected. And you can run all the cells now, and probably by the time I'm done talking, it will have completed the entire notebook. So with that, I will start the actual presentation. So why is the James Webb Space Telescope important? Well, ground telescopes tend to have their images distorted because of the Earth's atmosphere. So the clearest images we could possibly get would be from space telescopes. I hope people have heard of the Hubble Space Telescope. The James Webb Space Telescope is like that, except that it records images mainly in the infrared, and it allows us to see some of the very first galaxies in the universe and also measure the atmospheres of exoplanets. Another reason it's so important is that it was a collaborative effort between NASA, the European Space Agency, and the Canadian Space Agency. This is a graphic on Webb's journey. It took about 4 weeks to go from launch to its current position at L2. It then took about 6 months of commissioning to get the images science ready, and that is when we started seeing the first publicly displayed images. So what benefits do we get from James Webb? What you can see here is an image from Hubble of a galaxy, and it's visualized using JDAVIZ. And you can see it's quite fuzzy, but with James Webb, we can get more clarity. You could see in the picture before, you couldn't see through the gas, but James Webb with infrared can actually peer through that and see some of the stars and other features that are in galaxies or nebula. Here's another example of a galaxy cluster, again with Hubble, and here with James Webb. So I'm not sure if you can see my mouse here. So right here, I would direct you to pay attention here, because this is a galaxy, but the filter that was used is for a visual light. With this next filter, you can see it's a lot more vivid, and that is because this was taken using a filter in the infrared. We can see through the gas, we can see some of the stars that were in this galaxy. So what is JDAVIZ and how can we use it? JDAVIZ is an open source Python package used to visualize and analyze data from James Webb Space Telescope, among other telescopes. It is a single package that includes 5 preset configurations for now. That number may increase. One for images, for 1D spectra, 2D and 1D spectra, 3D data cubes, and for many 2D and 1D spectra. It can be run as a standalone application using the command line interface, or as a desktop application. It can be used in a Jupyter Notebook or Jupyter Lab, and it can also be embedded in a web page. And why did we build JDAVIZ? The existing tools were becoming outdated. A lot of astronomers, when I started at Space Telescope, were still using IRAF, which as of now is about 40 years old. So JDAVIZ was built to take advantage of the latest encoding standards, the latest framework being utilized by the open source community, which was Jupyter Notebooks. And since it's built using Python, we can use the latest science packages like AstroPy, NumPy, and Glue. And we also have a full team at Space Telescope of developers, scientists, and a UX designer. And we work with external contributors as well on front end, on our kernel. And we appreciate people even just opening GitHub issues and helping us detect bugs and constantly improve. Hoping some here will do that soon too. So to go back to what I was talking about before, filters. So how do filters help create the color images that we see? So each filter corresponds to a slice of wavelengths, and each wavelength specializes in seeing something differently. So some wavelengths are great at seeing the dust on the outside of a nebula or a galaxy, and some, especially in the infrared, can see through that. And JDAVIZ allows us to load all of those images representing each of those filters, assign a color to each, change the opacity, and essentially layer them on top of each other to create one colorful image. This is obviously not made by JDAVIZ, but this is an opportunity to just show a nice space image. This is the Southern Ring Nebula, and you can see some color composite happening here. This is done by the Office of Public Outreach at Space Telescope. They use a lot of specialized tools to get it to look like this. This is another image I hope people have seen. There is a Hubble image for the same area, but with the Hubble image, you can't see through some of the dark clouds. In that point here, we can see some stars inside of the gas, and here as well, we can see some stars being born. And that is enabled by the near-infrared and infrared filters or instruments on James Webb. So let's look at the interface for JDAVIZ. So here you can see InViz, which is our image viewer configuration. And what we have open right now is the data menu. This tells us what data has been loaded into JDAVIZ. The check boxes tell us what is currently visualized in that viewer. To the right of that, we can see zoom settings. So what's currently selected in the orange is our box zoom. To the right of that is a pan zoom button. To the right of that is the ability to create subsets, and we can use those to do further analysis using our plugins. So for example, with aperture photometry. At the top, we can see the information at mouse location. That's telling us the location and the value where our mouse is hovering. To the right of that, we can see that question mark button. That is our documentation. To the right of that is the logger communication. So anytime data is added, removed, changed, any plugin information is added, that will be in the logger communication. And finally, the visualization and analysis plugin tray. And each of these, each configuration has a slightly different version of this. But all of the plugins do some sort of visualization, like plot options lets us change the color of a layer or what the stretch looks like. And we also have analysis like aperture photometry. So where is everything located? JDAVIZ is on GitHub. It is a free and open source software. And like I said, we welcome all kinds of contributions. We have documentation on Read the Docs. Example notebooks are on GitHub in JDAVIZ and also in another repo called JDAT Notebooks. And we have example videos linked as well. I believe the latest ones are from this past spring. And what are we going to see today? So today's demo is going to be using InViz and one of its plugins to create a red, green, blue image of the Cartwheel galaxy. It's not going to look exactly like this. Like I said, the Office of Public Outreach has specialized tools. I think they use some Photoshop. But hopefully we can get pretty close. And I challenge everyone here to get closer than I can. I spent a few minutes, maybe more than that, trying to get as close as I could in my notebook. But I would be happy to be beat today. And we can do this demo using either user interface. I'll try to use that as much as I can, or we can use API. So I can take any questions now, and if not, we can move on to the demo.
Yeah, one question. It's more like a request. Could you show us the raw pictures for all the pictures that you showed? Like you showed the processed pictures, but
yeah.
It'd be nice to know what it was originally.
Yeah, thanks. I can do that during the demo, absolutely. Okay, so like I said, there is this cloud platform. I welcome everyone to give it a try. I was actually even able to get it to work on my phone, which I didn't think would work. I'm not promising that it will work great, but you might be able to see that final product. Instead, I'm going to run it locally. So I tend to use Jupyter Lab, so I will run that. And here you can see the notebook. Let me quickly just clear all the outputs. So here we will just import the modules we'll need for the notebook. I'm seeing the version of Jdaviz. If you're using the cloud, you will probably see about 3.10.2. I'm using a developer version right now. Hopefully that goes well, but that is the risk of a hot demo. So I already have all of the files locally. Again, this is the data directory for the cloud version. If you downloaded the notebook from the cloud, you'll need to go here and change this to be a local directory on your machine. I already downloaded the files. It might take a while. So that is this section of code here. Again, in the cloud, in the platform, I believe that is that's set as raw. If you download it, you can set it to code and then run it, and that will automatically download the files for you from MAST, which is the archive for Space Telescope images. Here I am just doing a batch load of all the files into InViz. And here I will show InViz itself. So few things here. I have about 6 images from NearCam. So that is the visible light with a little bit into the infrared. And I have 3 or 4 images from MIRI, which is the mid-infrared. When we load the images, there is like an estimate on the stretch, meaning the values coming from here. So if I mouse over, if I mouse over, you can see the value at the very top. The estimates for MIRI are not quite great. So you're going to just see like a white blob on the viewer, and that is why it is using it is because MIRI, we do not have the estimate set up for MIRI. So what I'll do first is go to orientation. So currently it is aligning everything by pixels. So if one of the images is like 1,000 by 1,000 pixels and another is 4,000 by 4,000, you're going to see the 1,000 by 1,000 here and 4,000 by 4,000 like that. If instead we align it by WCS, it is going to stretch those images so that they are covering the same parts of the sky. So if the 1,000 by 1,000 is covering the same feature in the sky, you'll see them overlaid on top of each other. Let's see. Choice a hot demo. There we go. So I was asked earlier to show what some of the raw images will look like. Let me just remove the MIRI images. So here you are seeing essentially a raw image from the telescope. This is just one of the filters. We have it set in our plot options currently that the color mode is color map. You don't need to know exactly what that means, but it essentially is just showing one of the images. So what I'm going to do first is change it to color mode. And if I can change the opacity here, you'll be able to see the images underneath. I believe F is at the top. So these are what the raw images would look like. So what I'm going to do now, so that we can get that pretty picture that we're looking for at the very end, I'm going to add the MIRI images back in. Make sure that everything is in color mode, which I believe it is. And what we're going to do now is assign the RGB presets. So what that does is it goes through each layer that is loaded in, and it assigns a color along the red, green, blue spectrum. With the images towards the red, further in the infrared spectrum, and images in the blue, images in the blue closer to visible light or even in the visible light. So we can still see that like MIRI blob over the image itself. What we can do there is go into the layer itself and manually change these stretch values. You can see we have a histogram here that shows where these values are. What I found is by taking this and just having this over that one really tall point in the histogram tends to improve things. But you can see it runs a little slowly. Invis is most performant with fewer images, but I think for the purposes of a demo, this will be fine. So I've used the UI so far. I'll quickly show the API. So we can access all the plugins by using the name of the configuration. So currently that's invis.plugins, and then you can access the plugins here and use our user API to do various things. What I'm going to do here is grab the plot options plugin. So we've already done these steps in the UI. So we've changed the color mode to be one color per layer. We've applied the RGB presets. So here, I mentioned earlier, I spent a little while trying to get the picture as close as possible. So here is using the code to get to that point. So I'm going to run this, quickly scroll back up, and we'll be able to see it live update each of the layers it's changing the stretch, so how much of that is being visualized, the opacity, bias, and contrast, and this is the best I could get. As I said, I welcome anyone else to try their hand at it. We can go down to the export plugin and then export this as a PNG. Overwrite the file I have on disk. Make sure this is the right one. And here we can see the image. So what I wanted to do is go back to the presentation here, put them side by side. So pretty good. Not as pretty, but in the neighborhood. So that is what you can do with JDAVIZ and with InViz. That is all I had as far as a demo goes. I'm happy to walk around and help anyone get this up and running, answer any questions about JDAVIZ or software development at Space Telescope. Otherwise, thank you all for coming.
Yes, thank you. Thank you for the presentation. I was just kind of wondering, because this is tools mainly used for visualization, right? So you mentioned that, for example, you can see calculate the atmosphere for exoplanets far, far away, you wouldn't use this tool for that, right? Or
So you probably wouldn't use IMVIS for that. You would use our other tool, which is SpecViz. So I will say, full disclosure, I'm not a scientist. I'm a software engineer. I work on a team with a lot of very talented scientists, and they've done their best to explain a lot of these things to me. Yeah, I think the tool for that would be SpecViz, where you are seeing the spectra or the spectrum from a certain point. And with that, they can see, based on these emission points, what elements are present in an exoplanet. So as the light from the star is going through the planet and hitting the telescope, they can analyze that to see what is that atmosphere made of.
all right, thank you.
Yeah.
Thanks for the presentation. Not really a question, but can you show again the QR code and the website where this can be found? It was pretty fast.
Oh, yeah. So, yes.
Thank you.
All of our documentation has all of the code examples, ways to install. So I highly recommend following that and getting a local install of JDAVIZ. That's going to work a lot better for you than the platform.
Thank you for the nice talk. I have more, I think, a technical question. What did you use to deploy it as a standalone application?
That is a great question. I was not as involved in that part. I know that we have, I believe, Voila was used. And we've investigated using Solara, but I don't think it's gone beyond that. I see Izaki is here in the stands. Yes, we work very frequently with Martin and Mario at the company to get that desktop application. You might know better than I how that process,
yeah,
but
I think recently we've been looking at using PyInstaller
yes.
to make a standalone executable, and then also PyQt is the other option. So we can inject Solara into, or this entire app in Solara into a web view in PyQt.
Okay, thanks.
Thank you. Sorry for putting you on the spot.
Hey, thank you for the presentation. That was really cool. So you've been playing with the UI first, and then showing you could do the same from the code. Can you, once you played with the UI, save it into some code in Ocel so you can easily replay what you've done?
Another great question. We have looked into state saving. We do not have something that the short answer is no. There's no easy way to take the exact state of the application at that time and save it and then reload it in that exact same configuration. You can use the API, like what I did in the notebook here. I spent a good amount of time fine-tuning the stretch vmin, vmax, and all these different parameters, and then I just did a quick for loop to print everything I had, copy that, and run it in the cell. Not ideal. But it is definitely something we're looking at and trying to implement. So I will leave it there, but I will hopefully have a better answer next time I come around for this.
Thank you.
Hi, thank you also for the very interesting talk. I was curious about the input format, the FITS format. I would have a couple of questions. Is it an industry standard? Is it compressed? Do you have issues with it? Do you have where did it come from? And can it be applied maybe in other domains like geospatial? Earth?
That would be fascinating if it could be. I know that it is an industry standard in the astronomy industry, and predates me by quite a bit. So I don't know what other applications, what other industries can use FITS. Have I had trouble with it? Not so much. It's not too bad. It's very helpful for sending the information for the image itself, along with all of the metadata. And we can actually see some of the metadata here. All of this information is also encoded in the FITS file, which makes it very helpful for visualization, especially with our other configuration for data cubes. It's important to know what units the data was recorded in, and what position in the sky. I do see some spatial. So maybe, I mean, it'd be fascinating if this could be used for GIS. That would be great. But I do not know any specific examples of that.
It does work on Earth. There are extensions for WCS on Earth, so
That's awesome.
Any other question? If not, then thanks our speaker again.